Hello and welcome to follow my course Introduction to Flow Mechanics. My name is Matti Ylitalo and I'm your teacher during this course. Let's have a look what we will learn during this course. Just a second, I'll put the presentation mode on. This course will consist of 6 videos. In this first video we will have an introduction to flow mechanics. And on the second video we will learn how we calculate the time to empty the tank. Then we will concentrate on heat transfer questions. Our fifth video is a special case. Then we will learn how we calculate the efficiency of fins. When we are talking about flow mechanics in industrial cases, our typical questions are pressure drops in duct flows, in pipe flows, heat transfer rate from surface or to surface. Also particle behavior is very important. It's often related to erosion question. Here we have a simple example. We have hot flow in pipe and around pipe is insulation. And we want to know what is the heat flux from fluid to environment. Basically it's very easy to calculate. It's only heat transfer coefficient times the surface area times the temperature difference between fluid and environment. But how we calculate that heat transfer coefficient, especially in case when we have a pipe wall and this insulation around that pipe. That's something what we will learn during this course. Then we in industry typically have this kind of questions. We need to calculate the time to cool down a vessel of, for example, water or warm it. If we have a fixed heat transfer unit there and it's having some maximum power, we need to calculate the time, how long time we will need to warm to get the temperature of a liquid to increase from one temperature to another. Fins, they are typically used to increase the heat transfer surface area. In many applications, like in cooling of electronics, we are using this kind of fins. And fins can be rectangular fins or so-called pin fins. Pin fins are seen on the picture on the right. We will learn now how we calculate the effectiveness of fins. During this course our focus will be in confined geometries, like ducts and pipes and so on. We will leave out some very important flow mechanical cases like mixing in atmosphere, mixing in seas, supersonic flows and so on. CFD is not included to this course, but it will come later. Let's take a couple of simple examples. This first one is a case when we have upward flow in duct and there are some particles and we want to know are these particles carried by this gas flow or are those particles dropping down. This is known as a terminal velocity problem. If we look at the force balance of particles, we have of course gravitational force, and because those particles are displacing some air, we will have also buoyancy force. And because those particles are moving, we have this drag force. And if we want to solve this force balance, we will end up to quite complex equation. And that's because there is this drag coefficient, which is a function of a Reynolds number. I asked ChatGPT to develop a Python code to solve this problem. ChatGPT is quite efficient tool to create Python codes for this kind of problems. I asked it to include different particle densities, and in this picture we can see the maximum particle diameter which is carried with that airflow. On x-axis we now have air velocity in meters per second. On a y-axis this maximum particle diameter, and there are different curves for different particle densities. The blue one is for particles having density 2500 kilograms per cubic meter, which is the density of typical sand particles. And the red curve there is for very light particles having density only 100 kilograms per cubic meter. And if we look at this picture, we can see that, for example, if we have air velocity 10 meters per second, that flow will carry heavy particles around 300 microns. And light particles, density 100 kilograms per cubic meter, almost 2 millimeter particles will be carried with that flow. When you're using this kind of method to calculate, you need to remember that this is valid for single particles. If we have a group of particles, those particles will be affecting on each other. And then this terminal velocity concept is not good choice. Then we typically use CFD. Let's take another example. We have a ball sinking in water. If we look at the forces affected on a ball, this is almost a similar case as in previous example. We have gravity force, and we have buoyancy force, and we have drag force. And if we make the force balance, we end up to the similar kind of equation as in previous example. Typically in this kind of cases we want to know the final velocity of these balls, and this can be calculated, but it's also quite complicated because we have that drag coefficient there, and it's dependent on Reynolds number. So I asked ChatGPT to develop a Python code to calculate also this case. I asked ChatGPT to include different ball sizes, and in this picture we can see the final velocity of balls having different diameters, and on x-axis we now have depth below surface. The blue curve is for ball having diameter of 1 centimeter, and the orange is for ball having diameter 0.1 meter, and the green one is for ball having diameter 0.3 meter. We can see that the ball will reach its final velocity quite soon, and after that the velocity will be fixed. If we look at ball trajectories, we see that after this initial period the trajectory is almost a straight line. In this picture we have time on x-axis and depth below surface on y-axis. And as in previous picture, the blue one is for small ball and the green one for ball having diameter 0.3 meter. When talking about balls sinking in water, there is always this very interesting question: will they sink or will they float? If the ball density is smaller than the fluid density, the ball will always float. The fraction submerged is dependent on density differences. On the box on the right side you can see an example calculation of ice cubes on water. The density of ice cube is 917 kilograms per cubic meter, and the density of water is 1000 kilograms per cubic meter. So the fraction submerged is almost 92%. You can visualize this case by adding some ice cubes on your water glass. Look at what happens. If the density of the ball is exactly the same as the density of fluid, the ball will float, but it is fully submerged. If the density of the ball is higher than the density of fluid, the ball will always go down to the bottom sooner or later. In the next video we will learn how to calculate the time to empty the tank. Thank you for watching and see you. Bye bye.